Chapter 7, Part 8, Dehydration Reactions. So, dehydration is usually called acid-catalyzed dehydration because this is going to happen in the presence of acid. So this is the elimination of alcohols. So for example, if you have a hydrogen beta to an alcohol and you add in a strong acid and heat it up, you can form an alkene and eliminate an equivalent of water. Tertiary and secondary alcohols dehydrate very readily and by an E1 mechanism. Primary alcohols can dehydrate by E2. It does not go through a carbocation intermediate and is also usually fairly slow. So the ease of dehydration goes along with our preferences for E1 or SN1. Tertiary alcohols dehydrate more readily than secondary, which dehydrate more readily than primary. The conditions required depend on the substitution of the alcohol. So for example, we have three different eliminations here. We start off with a primary alcohol. If we put it in concentrated sulfuric acid and heat it up to 180 degrees, we can get it to eliminate. Now, if we go to a secondary alcohol, we can either decrease the temperature or we can decrease the concentration and strength of the acid, or maybe do a little bit of both. So you can take a secondary alcohol and put it in only 85% phosphoric acid, heat it up to around 170 degrees, and get it to dehydrate. If you have a tertiary alcohol, you can put it in watered down sulfuric acid, so 20%, and heat it up to only 85 degrees Celsius. If you were to put this in concentrated acid, you could drop the temperature even lower. So let's take a look at the mechanism here. So the first step is to protonate the alcohol. So I used generic symbol for acid, generic symbol for heat, so that none of our conditions here are specific. So the alcohol gets protonated. In step 2, water leaves and a carbocation is formed. So water takes the electrons in that bond and goes. So that we now have a carbocation and an equivalent of water. The carbocation can rearrange if appropriate. And then lastly, we deprotonate to form the alkene. So we pull off a beta proton. The electrons between the carbon and hydrogen go to create the pi bond, and we end up with our product. So let's take a look at rearrangements in dehydration. Since the E1 mechanism goes through a carbocation, rearrangement is perfectly possible. So in this mechanism, the alcohol is going to pick up a proton from the phosphoric acid. And then water is going to leave. Giving us a carbocation that can rearrange. So this carbocation is secondary and it is next door to a quaternary carbon. So one of these methyl groups can shift over in a methyl shift. Which gives us a new tertiary carbocation. From here, we can pull off the nearby beta proton and form the alkene. So the rearrangement is important because if you didn't do that, you would have ended up with this alternate product, which would be a very, very minor product if it formed at all. Let's take a look at the dehydration of primary alcohols via the E2 mechanism. So if you have a primary alcohol and you put it in acid, it is going to get protonated just like any other alcohol would. The difference here between the primary alcohol and the other examples we saw is that if the water were to leave, we would be left with a primary carbocation. So we are not going to do that. Instead, we're going to have to push the water out. So here you could use the conjugate base of sulfuric acid, or you could use another equivalent of the alcohol. Which I like a little better because it's a stronger base than the conjugate base of sulfuric acid would be. So we form the double bond and we kick out water. And we end up with our alkene plus water and also an equivalent of the protonated alcohol, which we needed anyway because now we could go ahead and continue our process. And we also just made water, so we could even start to switch up our base if we wanted. Okay, let's do a practice problem. Go ahead and pause the slideshow and think about this one for a second, and then we'll come back together and do it. Okay, welcome back. So the alcohol is going to pick up a proton from sulfuric acid. And this is a secondary carbocation. Anytime we make a carbocation, we always need to ask ourselves, is this the best carbocation I can make? And if it is not, try rearranging that carbocation. Now there are two rearrangements that you could do. You could shift the methyl group over if you wanted, but the better rearrangement is going to be a ring expansion. So opening up that ring and creating a 6-membered ring. So this still upgrades us to a tertiary carbocation, and it also upgrades the ring from a 5-membered ring to a 6-membered ring. And now we can finish our elimination. There are two possible beta protons here, but pulling off this one instead of the one that's on the methyl group would give us the more substituted alkene.